Hello everyone, I appreciate the opportunity to share our recent work on the regulation of beta oscillations in the global Pallidus external segment. Despite that, there are 5 frequency bands commonly observed in brain oscillations. Here, I would like to concentrate on the beta oscillations, which have been suggested to play crucial roles in perceptual, cognitive, and motor processes, and may be recruited in different brain regions for different tasks. In addition, growing evidence has suggested that beta oscillations are closely associated with Parkinsonian disease, and the abnormal cortical base ganglion circuits should be responsible for these PD-related beta oscillations, especially the GPE may be the center of origin. On the other hand, large number of studies have confirmed that deep brain stimulation can effectively improve the symptoms of PD and decrease these abnormal beta oscillations. However, few studies pay attention to functional roles of the GPE DBS. Accordingly, we designed a closed-loop DBS to investigate related mechanisms underlying the GPE DBS. We used the East-Curvature model to build the GPE neural network model, which contains 1,000 randomly connected neurons. The interactions between neurons are mediated by chemical and electrical synapses, and the corresponding connection probabilities are 1% and 0.5% respectively. The model parameters are adapted from previous studies and given in the table. To quantify the neural activation level of the GP neurons, we computed the synchronization index and the oscillation index. Here, we defined the LFP as the sum of neural synaptic currents and took the feedback LFP of GP neurons as a stimulus current. Notably, we considered 2 control manners, that with and without feedback delay, and used a scale factor to adjust the feedback LFP. In the case without delay, as shown in the right figure, we could observe that both the synchronization index and oscillation index gradually decrease with increasing the scale factor. Moreover, we calculated the spike and LFP to show the dynamic variations of GP neural activity, and found that increasing the scale factor can push the synchronized GP neuron into the random fine state and remarkably suppress beta oscillations. Then, the time delay of feedback LFP were incorporated. Similarly, we also calculated the oscillation index and the synchronization index of GP neurons in the 2-parameter space. As shown in the figure, the GP neural network shows strong beta oscillations with small values of the scale factor, where time delay has limited effects on these beta oscillations. One, gradually enhancing the scale factor, the synchronized fine of GP neurons can be pushed into random fine state, and the fluctuation amplitude of LFP can be remarkably reduced as well. Consequently, the beta oscillations would be significantly weakened in this case. In addition, based on the oscillation index and time frequency analysis, it is reasonable to conclude that increasing time delay contributes to regulating beta oscillations by changing scale factor. However, it should be noted that enhancing the value of time delay may lead to large fluctuations of LFP, high synchronization of GP neurons, and low-intensity gamma oscillations. Overall, both the time delay and the scale factor have influence on the regulation of beta oscillations in the GPU neural network. In summary, the established GPU neural network model can generate beta oscillations. Both a delayed and non-delayed closed-loop DBS can effectively modulate beta oscillation in the GPU neural network. These findings may provide a new DBS strategy to the treatment of PD. At last, thank you to my research collaborators and thank the support from the National Natural Science Foundation of China. Also, thanks for your attention.